Okay, at the end of our lesson here, we're going to see that very often our surface might just be defined in terms of x and y. So what if our surface just has a function g of x and y? We'll use x and y as parameters and get something very, very similar. You might remember from an earlier section that the cross product of r sub x and r sub y would be the negative partial derivative of g with respect to x for the I component, negative partial derivative of g with respect to y for the j, and then a 1 for the k. When we found the length of that applying the Pythagorean theorem, that's where that square root of partial derivative of g of with respect to x squared plus the partial derivative of g with respect to y squared plus 1, that's where that came from. But suffice it to say, if you just want to memorize this really slick formula right here, when you do your dot product, you'll see that P, the x component of your vector field's definition, when it's multiplied to your surface's partial derivative with respect to x, you'd have a negative right there. You'd say plus multiply q times negative partial derivative of g with respect to y. You could see that showing up right over here. And then your r gets multiplied to 1. You have this very simple and nice definition for flux. What are we getting at? We're seeing this. We can see that P is an x component for the vector field, and it's multiplied to a partial derivative with respect to x for the surface, and there's a negative. The Q right here is a y component for your vector field. It gets multiplied to that partial derivative of g with respect to y, the surface's partial derivative with respect to y. Both of those are negative, and then you just plus that, add that to r, which is the k component of your vector field. Wonderful, wonderful way to get through this. Again, this formula is assuming upward orientation. You'd have to multiply by a -1 for downward orientation. Upward orientation means that your normal vectors are pointing up. Similar forms could be worked out in terms of having functions in terms of other variables, in terms of x and z or y and z. But let's take a real quick peek right here at our last problem and see what's going on. We can see that really we have our surface. There are two parts. There's S1 and there's S2. So this region that we're talking about, it's this boundary bound by this paraboloid. That's what we'll call S1. And the plane S equals 0, that's what we'll call S2. And altogether, that would be the entire surface. So let's just pay attention to S1 first and see how that's coming out. You could say right here, Z is your 1 minus x squared minus y squared. Guys, that's really what we have for our g of x, right? We could say z is equal to our 1 minus x squared minus y squared. That's like your g. And we very well will want to find the partial derivative of g with respect to x. Let's do that real quickly. What do we get? Simply a -2x. We'd want to take our partial derivative of g with respect to y. Likewise, we'd get -2y. And, at this point, it's actually pretty nice where we can, use this shortcut formula that we're going to be able to be using. Our f, is going to be a vector, of course. Here's your p, q, and your r, your p, q, and your r, guys. Your p is y, your q is x, your r is z, but guys, z on this surface, remember what's going on. First, you want to have your parametric form for your surface, but you always apply that parametric form to your vector field. So what that really means is that your vector field is parametrically defined in x and y. That means my z, in this case, becomes 1 minus x squared minus y squared, because for S1, every z value comes from that definition. So this is really your P, your Q, and your R. Now, what we can do right up here is if you look at the very top of the screen, we can say that this flux right here is going to be a double integral, and we're going to say negative P times partial derivative of g with respect to x. So we'll go negative P, that's negative y, writing up above here, and then we'd have partial derivative of g with respect to x. That'd be negative 2x right here. Now I'm going to say minus a q. Well, the q is going to be your x, and then you're going to be multiplying by the partial derivative of g with respect to y. Well, we just figured that out. That's negative 2y. And then we'll say plus your r value. Well, your r value is 1 minus x squared minus y squared, right? And then we've got our dA, and here's our region D. So at this point, guys, what you can see more or less is that this surface S1 is defined in terms of x and y. But x and y values, wow, my computer keeps doing this. Let me just jump to my mouse here. My x and y values are only going to be from really this projection down below. The only x and y values I can be using to graph this paraboloid is coming from where the x and y points would be projected onto the plane z equals 0. And at this point, you could begin to look at that and say, well, wow, I could definitely, clean that up some. But if you're looking at that little floor down there, I hope what you're looking at is this, that's a circle, isn't it? If you were to take z equals 1 minus x squared minus y squared, if you were to let z equal 0, it only would take you a minute to see, well, that's equivalent to having x squared plus y squared equals 1. That's that green circle on the floor. Now, that can help us in terms of finding boundaries for x and y. Now, you can clean this up a little bit, by the way. I think you can see that a negative times a negative is a plus, and you can do this. You're going to have a 2xy and a 2xy. That's going to be a 4xy. And right here, you'd have a 1 minus x squared minus y squared. So, we're getting very, very close here to wrapping this up. But to find boundaries, I think there's a much easier way to talk about the boundaries for x and y. And that's converting it to, what do you think? Polars. Absolutely. You want to go to polars. So for your polars, if we look at this in terms of polars, what you're going to see is that, wherever we have an x, we're going to have an r cosine theta, and y will be r sine of theta. And this is really like 1 minus x squared plus y squared right here. So we could definitely start cleaning this up a lot. And you know what? I didn't start the video, did I? Here we go. That's all right. Just hoping that Reshma can get. All right, so as we go to polars, our x is going to be r cosine theta. Our y is going to be r sine theta. And this is ultimately 1 minus x squared plus y squared. So, hopefully you can see we're going to have an r squared cosine theta sine theta. And then you've got your 1, but I hope we all know that this is going to be minus r squared. X squared plus y squared is really just going to be a minus r squared. But our dA, our dx dy is going to change to an r, dr, d theta. And guess where our r is going to be spanning from? From 0 to 1. And guess where our theta is going to go from? 0 to 2 pi. And we're going to just let the TI-89 help us out with this, okay? So we'll pause that. My apologies, I forgot to write the 4 right over here. Special thanks to Nitty for pointing that out again. But, because that got copied in there. But again, once you let this, just get punched out on the 89, and we distributed in R, everywhere we had R, we treated that as if it were an X. So really we had like a 4x to the third, cosine of y, sine of y, and so forth. You'd wind up getting pi over 2. So thankfully, nicely, you get pi over 2. But before too long, somebody's going to say you're not done. Isn't there another part of the surface? Yeah, there's S2. Oh boy. All right, so you've got S2, and you could say, well, let's see here. S2, though, is rather interesting, isn't it? S2, by the way, it's got negative orientation. We're going to have to multiply by -1 at the end. You might say, how do you know you've got negative orientation? Your normals aren't pointing up, they're pointing down. So that's something real tricky. Sometimes it's almost like, wow, how come I got a positive answer versus a negative? Tell me about z. What's z? Z equals 0. And I can tell you this much. If g is equal to 0, the partial derivative with respect to x, the partial derivative with respect to y, that's going to be 0 also. Wow. Well, I'll tell you what. F, your function is y, x, and z, but now your z is 0. And here's your P, here's your Q, here's your R. Well, as we work this thing out, and you can see it's right at the top of the screen here, so we try to work out the rate of flow down below here. We're going to say, well, I need to go negative P, so that's negative y, times a derivative of g with respect to x, that's 0. Minus, I've got my q, that's x, times the derivative of g with respect to y, that's 0, plus r, that's 0 too. Guys, we can get upset about this for a minute, but guess where this thing's going? This is going to 0. So guess what? The total rate of flow is really pi over 2 plus 0. Final answer, thank goodness, is just pi over 2. Okay?